Welcome to the video on the organization of the periodic table and electron configuration. The periodic table is pretty awesome the way that it's put together. We can actually consider this almost like a cheat sheet in this class. Because of the way that it's organized, you can learn so much about an element. Elements with very similar chemical and physical properties are grouped together, and they're arranged completely in order of increasing atomic number. Remember the number of protons. So the very first element of the periodic table here has one proton and one electron when it's neutral. The second one, atomic number 2, helium, has 2 protons and 2 electrons. And you just keep walking through the periodic table in order by atomic number. The horizontal rows are called periods, and the vertical columns are called groups or families. In the above periodic table, it is color-coded. The blue elements are good conductors of heat and electricity, and those are considered metals. The yellow elements are poor conductors of electricity and heat, and those are considered non-metals. And in between those two, metals and non-metals, we have the metalloids, which have properties that are in between metals and non-metals. Now, of course, we're going to have names for some of these elements and groups of elements. Group 1, shown as red here, is called the alkali metals. Group 2 are the alkali earth metals, in orange. Group 5 are called the nintogens, in fluorescent green. Next in blue, we have group 6 are called the chalcogens. Group 7 are called the halogens. And of course, group 8, in royal purple, are the noble gases. All the elements on the periodic table ultimately want to be like a noble gas. Then in the center, takes up actually most of the periodic table, is the transition metals. Then down at the bottom, which actually, when you see a full periodic table, these get inserted right here, and we'll see that in a little bit. But the elements in pink called the lanthanides, and these are called the actinides. Just some terminology that you'll need to know. Remember, in a previous video, we talked about ions, where elements lose and or gain electrons compared to their number of protons, and then they become charged. And remember, just a second ago I told you that everybody wants to be like group 8. Everybody wants to have an electron configuration like group 8. So it turns out there's some general trends in the periodic table as to what kind of ion they will become. Group 1 over here will typically become +1. For example, lithium loses 1 electron. It becomes the electron configuration of the atom just below it in atomic number and of the noble gas. And in a few minutes, we'll talk about electron configuration. But you can see that when lithium loses 1 electron, instead of 3, it has 2, and then it becomes the one before it. And +1 because it has 1 extra proton compared to electrons. So everything in group 1 becomes +1. So it goes in line that group 2 is going to become +2 because it needs to lose 2 electrons to get back to the noble gas. Group 8 is the noble gases, and they are good to go. They are absolutely happy the way they are. They have a full valence shell. They have a full octet. They are very good the way they are, so they will not typically gain and or lose electrons at all. Group 7, however, becomes negatively charged because if they gain just 1 electron, then they become that noble gas configuration. Group 7 typically has a -1 charge. Group 6 typically has a -2 charge. Group 5 typically has a -3 charge. And sometimes in group 3, we can see a +3 charge. In all cases, these elements want to get to a full valence shell, and they want to get to noble gas configuration. The transition metals in the center here are a little tricky because they can often become +1, +2, +3. So many of them have multiple options in terms of the ions that they are. And shown here are the typical ion charges for a few of the transition metals. Iron can be +2, +3. Copper can be +1, +2. Zinc is typically +2. Silver is +1, and so on. So the next thing I want to talk about is electron arrangements. So where are those electrons that we just talked about being present? Electrons revolve around the nucleus at different discrete energy levels, or shells, and each shell has a definite energy. And so you can see as we move out, energy level 1 has 2 electrons possible, energy level 2 has 8, energy level 3 has 18, and energy level 4 has 32 possible electrons. And that comes by the equation 2n squared, where n is the shell number. If we think about sodium and draw its electron arrangement in this way, sodium, if you look on the periodic table, has atomic number of 11, which neutral element will also have 11 electrons. So in the first energy level, we have 2. In the second energy level, we have 8. And so that is a total of 10. In our third energy level, we have 1, giving us a total of 11. And so that is the electron arrangement for sodium that is neutral. And if we do the same thing for sulfur, sulfur has an atomic number of 16. And so we need to place 16 electrons around. The first energy level is 2. The second energy level is 8. And then put 6 in that outer energy level. That would be the electron arrangement for sulfur. So you've heard me refer to the term electron configuration, and that is what we're going to talk about right now. And the definition of that is how the electrons are distributed among the various atomic orbitals in the atom. We said hydrogen just has 1 electron. Where does that electron go? Below here is how we draw electron configuration. So first we have the energy level, and that's going to relate to the period on the periodic table. And then we have the shape of the orbital, and in just a second we will talk about what that means. And then we have the number of electrons that are in that orbital. Talk about the shape real quick. When we have 2 electrons, that's going to be spherical in shape. So the shape just means the probability that the electrons will be located there. And that is what we call the s orbital. And when we have 6 electrons, these are going to be taking the shape of dumbbells. And it's hard to see in this diagram, but these dumbbells are along the x-axis, these are along the y-axis, and these are along the z-axis. So we have these 3 dumbbells that go in different orientations for our 6 electrons in the p orbital. And then down here, we have the d orbital, and the d can accommodate 10 electrons. And here is the shape and or the location of the electron in terms of probability, and that's the D. We have the S, which can fit 2 electrons, the P, which can fit 6 electrons, and the D, which can fit 10 electrons. And so when we have our electron configuration, here's the energy level or period, here's the orbital shape, which we just talked about, and then here's the number of electrons that are in that orbital. Before we go any further in talking about electron configuration, let's talk about a couple other principles and rules that we need in order to do electron configuration correctly. The first is the Aufbau principle, or the building up principle. This states that our electrons have to be added to the atomic orbitals based on their energy level, starting at the lowest energy. So this principle tells us that our electrons are put into the orbitals starting with the lowest energy first. Here is a schematic showing the energy levels of the different orbitals. The lowest energy is at the bottom, and as we go up this schematic, we can see we're increasing energy levels and getting farther and farther away from the nucleus. And that's the Aufbau principle. The second piece of information that we need to think about is Hund's rule. And Hund's rule tells us that subshells with parallel spins are the most stable. Another way to say Hund's rule, for orbitals that are equal in energy, the shells need to be half filled completely before we go back and start putting a second one in. If you look at the example on the bottom right here, this is the electron configuration for nitrogen. Nitrogen is 1s2, 2s2, 2p3, and the top depiction of the electron configuration is actually the correct one. That is Hund's rule. That 3 degenerate or equal in energy p orbitals will be half filled each before any of them double up like the bottom example. The bottom example is not correct. So remember when I told you that the periodic table gives us a lot of hints about how things are going to be in terms of its organization? Shown here is an example of the periodic table that really helps us with electron configuration. In this schematic, we can see the elements going in order of atomic number, and we know exactly what shells to fill first. The 1s, and then the 2s, and then the 2p, and then the 3s, and the 3p, and then the 4s, and then you see we go back to the 3d, and then back to the 4p, 5s, etc. So this table is really amazing, and it really helps us see how the orbitals are filled. This is where hydrogen would be right here. And hydrogen's electron configuration is 1s1. And then helium over here would be 1s2. Here's the second period, which is going to be our 2s. So this would be 2s1, 2s2. And then over here we have 2p, 1, 2, 3, 4, 5, 6. So remember, our p orbitals can hold 6. And so this purple block is our p electrons. Remember, our s can hold 2. So here is our s block. And then our d orbitals can hold 10. And that's right here. We have not talked about F yet, but if we did want to have electrons in F orbitals, those are going to be down here. The periodic table is ordered according to chemical and physical properties. It's also key in helping us decide the increasing electron energy as we move through the periodic table. So let's get right down to it and see if we can draw out and determine the electron configuration for some of these atoms. Lithium has the atomic number of 3, and when it's neutral, it will have 3 electrons. And so we fill up the 1s because that's the lowest energy. So we have 1s2, and then we have 1 electron in the 2s. So the electron configuration for lithium is going to be 1s2, 2s1. Beryllium, we add 1 more electron, so it becomes 1s2, 2s2. So now we're going a little deeper and we're going into the p orbitals with boron. So we have 1s2, 2s2, and then we have 2p1. Carbon, we add another one, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3, shown right here. And again, Hund's rule, we're going to half fill each orbital that's degenerate before we go back and double up. Oxygen, 1s2, 2s2, 2p4, and that's shown here. Fluorine, 1s2, 2s2, 2p5. Okay, we're getting close. And then neon, that's our noble gas. That has a full valence shell right here, but it is 1s2, 2s2, 2p6, and that's our noble gas. Now, one little thing that we could do if we're going to try to do a little bit of a shortcut is draw the condensed electron configuration. 1s2 is actually equal to helium. We can use square brackets and include helium in place of 1s2. Now it turns out we can now use neon in place of 1s2, 2s2, 2p6. For class, I would like you to determine the electron configuration for calcium and for sulfur. So far, our examples have focused on the S and the P electrons. So let's think about D. If we move down the periodic table to elements that include electrons that are in the d orbitals, if we do scandium, then we have argon plus 4s2 and then 3d1. And then if we do titanium, it's going to be 4s2, 3d2. And then if we do vanadium, it's going to be 4s2, 3d3. In terms of energy, that the 3d and the 4s are very close to each other. There's not a big difference between those energies. In the next example, chromium, we can actually, in order to half fill the Ds, we have access to that 1 electron that's in the 4s. So this one would be argon, and then we have 4s1, 3d5. And so that phenomena happens whenever we have the d orbitals being half filled, and then it happens again when it becomes full. So for copper, we're going to have argon plus 4s1, 3d10. And so if we go back to our periodic table, we have to remember that this row right here is special, and this row right here is special, in that the electron configuration has the d orbitals either half filled or completely filled, and the s orbital then not completely filled. The last thing I want to talk about in this video is ion configuration. This is the electron configuration of an ion. So if we have an extra electron with a negative charge, or we're missing an electron with a positive charge, we're going to have to reflect that in our electron configuration. For example, magnesium is in group 2, so it's very typically going to have the charge of Mg2 plus, in which case we have 2 less electrons than we would typically have in magnesium. If you look at the periodic table, magnesium has an atomic number of 12, and so that means if it's missing 2 electrons to be a positive 2, that would mean it would have 10 total electrons. Drawing the electron configuration using our shorthand, the noble gas right before it is neon, so it would be neon, and then after neon, if it was magnesium, we would have 4s2, but because it's positively charged, those 2 electrons are missing, and so we actually now have the noble gas configuration of neon. We look at our second example with oxygen. Oxygen is in group 6, and so it's typically going to have a -2 charge, but oxygen's atomic number is 8, and so if we have 2 extra electrons, that's also going to be 10 electrons. Oxygen has an electron configuration of the noble gas neon when it has a -2 charge. And for clarification, both of these would be 1s2, 2s2, 2p6. And it turns out that these 2 species, magnesium and oxygen, in their ionic form of the Mg2 plus and the O2 minus, are what we call isoelectronic. And what that means is that even though they are different atoms with different atomic numbers, their electron configurations are all the same. These isoelectronic species are going to typically have the electron configuration of a noble gas because everybody strives to have that full valence shell. So if we just for a second take a look at the transition metals and what happens when we have electron configuration of ions that are in the transition metals, we'll look at iron. If we draw out the electron configuration for iron uncharged, we have an atomic number of 26, and our closest noble gas is going to be argon. And so once we have argon, we're going to look at period 4, and we're going to have 4s2 and then 3d6. It turns out because the 4s and the 3d energy levels are so close, sometimes this electron configuration is written this way. And I would accept either answer here for iron, uncharged. So if we then think about iron 2 plus, so this is going to have 2 less electrons than regular iron. And so it turns out that those electrons get removed from the s orbital. And so the electron configuration for iron 2 plus is going to be argon 3d6. And continuing in that same fashion for iron 3 plus, we're going to need to remove 3 electrons. So we remove the 2s electrons, and then we actually remove 1 of the d electrons. So iron 3 plus is going to have an electron configuration of argon 3d5. So for practice, I'd like you to take a look at this practice page in your notes and try to write both the full electron configuration and the condensed electron configuration for these atoms and ions. Electron configuration is quite straightforward. The periodic table gives us so much insight, so use the periodic table for sure as you're doing this. And like always, practice makes perfect. So practice, practice, practice. Okay, good luck.